Okay, we are in Algebra 2, Mod 8. Keep on rolling here in our chapter on sequences and series. Today is Wednesday, May 6th. So top left corner of your paper, Wednesday, 5/6/20 for the date. Again, hopefully you're keeping a nice, neat, organized notebook that you can carry forward into next year with all these topics listed in case you need to refer to them. The title of today's notes, it almost sounds like an oxymoron here. It says the sum of an infinite series. So sum of infinite series is our title. And again, think about what that says. If the series, which is a bunch of numbers with, a number plus a number plus a number plus etc., if it's infinite and goes on forever, how could it actually have a sum? So put a little arrow down from the title and go ahead and pose this question as the first thing in your notes and write down, if a series is infinite, which of course infinite means goes on forever, 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 forever. I'm going to have a number plus a number plus a number plus another number plus another number. And if it went forever, can it actually have a sum? And can you arrive at a final answer? Now, of course, your instinct is telling you no, and a lot of times that instinct is correct. For example, okay, guys, start out on your paper with these first two examples here. Example number 1, go ahead and write 1 plus 4 plus 7 plus 10 plus ... Now, would you agree that is a what if you had to describe it? It's an infinite series, right? Because it has ... and I'm going to keep going forever. It is a series and not a sequence because I'm adding the numbers. There's not commas in between, there's pluses. So if I'm supposed to take 1 plus 4 plus 7 plus 10 plus, and then keep on going, by the way, that is what? An arithmetic series, right? You should be good at the terms arithmetic and geometric. Why is that arithmetic? Because I start with the number 1 and I add 3 to it to get 4. I add 3 to it to get 7. I add 3 to it to get 10. So this is an arithmetic series that goes on forever, whose common difference is 3. If I told you to add all them numbers together and give me a final answer, well, 1 plus 4 is 5, plus 7 is 12, plus 10 is 22, plus 13 would be 35, plus... Obviously, if I kept going forever, I would never arrive at a final answer, would I? Because the numbers keep getting bigger and bigger, and it would never arrive me at a final answer. So if I ever have an arithmetic series and the numbers are getting bigger and bigger, in other words, the difference is bigger than 1, I have a positive difference, there's no way you can get a sum. It would be sumless. Agreed? It would be a sumless series. You can't arrive at a final answer. Wouldn't the same be true if it was arithmetic and the numbers were getting smaller? Now notice here, 8, then 5, then 2, then -1, then, I'm adding -3 each time, so my difference is negative instead of positive. Agreed? Well, if I added these numbers, 8 plus 5 is 13, plus 2 is 15, minus 1 is 14, minus 4 is 10, minus 7 is 3, minus 10 would be -7. Then I add another number, and it keeps getting bigger and bigger and bigger in the negative direction. The point is, if I added these numbers forever and kept on going and never stopped adding them, again, I couldn't arrive at a final answer, could I? This also would be... Do you agree? Sumless. So basically, I've used these two examples to come up with a really important fact. Go ahead and put a big star on your paper and write down what fact, if I ever have an infinite arithmetic series of any kind, if you notice, that's arithmetic because I keep adding the same number every time, then that series will be sumless and I won't arrive at a final sum. Agreed? So every arithmetic series is sumless. Exclamation point. Okay, guys? So on your little homework assignment, when I give you a series and say, what's the sum of the whole thing? If you see that it's arithmetic, then automatically it's sumless and doesn't have an answer. Okay? So the question now is, what if it's geometric? So let's go to this example. 1 plus 2 plus 4 plus 8 plus ... What's the pattern here? I'm timesing by 2, timesing by 2, timesing by 2. Remember, anytime you multiply by some number to get the next number, that was geometric. This is a geometric series, and the ratio would be what? 2. Remember, because I'm multiplying by 2 every time. Well, guys, isn't the same thing occurring here? If the numbers keep getting bigger and bigger, my next number would have been what? 16, then 32, then 64. If I told you to add and sum, what's the sum of the whole thing? Well, 1 plus 2 is 3, plus 4 is 7, plus 8 is 15, plus 16 would be 31, plus every time I add a number, I get a bigger and bigger answer. I could not arrive at a single sum because it just keeps on growing and getting bigger. So, if my series is geometric, and the ratio is greater than 1. In this case, I was multiplying by 2, or maybe 3, or maybe 4, or maybe 10. If it's a geometric series and the ratio is greater than 1, and the numbers are getting bigger and bigger, then also it's going to be what? Sumless and doesn't have an answer, does it? And then finally, oh, watch this, interesting. What if I have a series that says 1 plus 1/2 plus 1/4 plus 1/8 plus 1/16 plus etc. And I said, add all those numbers together and tell me what you get. Notice. Okay, first of all, what's the pattern? Aren't I taking the 1 and I'm timesing it by 1/2 to get 1/2? 1/2 times 1/2 is 1/4. 1/4 times 1/2 is 1/8. 1/8 times 1/2 is 1/16. The numbers are getting smaller and smaller and smaller until, now do you agree the next number would be 1/32nd, then 1/64th, then 1 over 128? So eventually I'm getting numbers, fractions that are so small. I would eventually get to 1 over 2 million. Well, 1/2,000,000th is such a tiny, insignificant number, it's as if I'm adding 0 every time. So guys, this is a geometric series. The ratio is less than 1, isn't it? I was multiplying each time by 1/2, and the numbers I'm adding are getting so small, it's just like adding 0 every time. So I can actually arrive at a sum. Because, guys, the rule in every level of maths from Algebra 2 and beyond, all answers are rounded to the nearest 3 places. So eventually, when I add 1/2,000,000th to this number, yes, it gets a little bit bigger, but way down in like the 15th decimal place. It'll never, ever change the first 3 decimal places, and I'll actually have the same answer every time, even though I was adding numbers forever. All right, so bottom line is, if your series is geometric and you look and say to yourself, oh, my ratio is, in this case it was 1/2 or 1/3 or 1/4. If the ratio is less than 1, then it has a sum, exclamation point. And to figure out what is the sum of that infinite series, if I add all them numbers together, what would I get? I've got a formula for you. Now, I know you're sick of formulas, but guys, this formula is easy. You put capital S. Now, there's no sub n here. I'm not trying to find the sum of the first 8 numbers or the sum of the first 10 numbers. I want the sum of the whole thing. To find the sum of the whole geometric series, when the numbers are getting smaller and smaller, in other words, when the ratio is a fraction smaller than 1, it has a sum, believe it or not, and the sum is found by just doing a sub 1 over 1 minus r. So you take the first number and divide it by 1 minus whatever the ratio is. So guys, for this particular example right here that I just had, if I said, what's the sum of the whole thing? Instead of saying, oh, it's sumless because it goes forever, you're going to take A1, the first number, which is 1, divided by 1 minus whatever your ratio is. Well, remember, the ratio was what here? We were multiplying by a half. Obviously, that gives me 1 over, what's 1 minus 1/2? 1/2. And guys, that would give me 1. You change division to multiplication and flip the bottom number over. So it really is 1 times 2, which would be 2. So I guarantee you, if you add 1 plus a half plus a fourth plus an eighth plus a 16th and kept on going and added all them numbers together, you would arrive at the number 2. And even though you'd go forever, you would never get an answer bigger than 2.000. It might be 2.00001 eventually, but that doesn't count. That's insignificant. It would never change from the answer of 2. Interesting. Okay? So, a couple examples and we're done. What if I had that sequence, or series of numbers right there? 0.3 plus 0.03 plus 0.003. Now, first of all, if you looked at this series and had to describe it, how are you going from this number to that number and from this number to that number? Aren't you multiplying by 0.1? Let's try it. I'm going to get my calculator. I'm going to push 0.3 times 0.1 and I'm going to get 0.03. If I take 0.03 times 0.1, I get 0.003. So this is a what? Geometric series whose ratio is 0.1. Agreed? And since that's less than 1, it has a sum. Oh, it's geometric. The ratio is less than 1 because it's 0.1, right? So it has a sum, even though it goes forever. So to find the sum, I'm going to go to this formula. A1, what's the first number? 0.3 over 1 minus my ratio, which is 0.1. So do you agree that's 0.3 over, 1 minus 0.1 is 0.9. So pull out your calculator. 0.3 divided by 0.9, enter. And I get 0.3333, etc. Actually, I should write 0.333 because, again, all answers are rounded to the nearest 3 places. Okay? All right, last example and we're done. Stay with me here. Okay, if this is you doing your assignment, you're going to look at your infinite series and your first thought is to decide what kind of series it is, guys. If I look, and this is an arithmetic series where I keep adding the same number every time, then you're going to write sumless. If it's geometric, because I'm multiplying by the same number every time, and the numbers are getting bigger and bigger, that's sumless. So you'll have some answers that are sumless. The only series that actually has a sum when it goes forever is if it's geometric and the ratio is smaller than 1. So look at this problem here. What is happening to get from, so it's pattern recognition. What are you doing to get from one number to the next? Aren't we multiplying by 1/2, right? It shouldn't be that hard to see. What's 7 times 1/2? 7 over 2. Times 1/2 is 7 over 4. Times 1/2 is 7 over 8. Times 1/2 is 7. Oh, this is geometric and the ratio is a half, isn't it? That's smaller than 1. So this thing actually has a sum even though it goes forever. So if I added all these numbers together and kept on going forever, what answer would I get? Well, if I again use A1 over 1 minus R, my first number is obviously 7. I'd have 1 minus, what was my ratio? 1/2. This is easy, isn't it? I have 7 over, what's 1 minus a half? A half. Now guys, 7 divided by a half is not 7 1/2. Doesn't that mean take 7, division changes to multiplication, and I take the bottom number and flip it over? Oh, believe it or not, 7 times 2 gives me a sum. If I added all those numbers together, I'd get 14. You would never ever get 14.1. Ever. Even if you went forever, that answer will not change. The only thing that would change is all the decimal places after 3 places would eventually change to bigger numbers, but those don't count. Okay? So your assignment, real simple here. Go ahead and hit pause on your video. You've got these 6 series. Go ahead and copy all 6 of them down. 3 plus 5 plus 7 plus 9 plus ... All I want to know is what's the sum of each series. If I did add all those numbers forever, what sum would I arrive at? Okay? So you've got 1, 2, 3, 4, 5, 6 of them. Your job basically is to look. If your thought is, ooh, they're adding the same number, that's arithmetic, then you write sumless, right? If they're multiplying by the same number every time, and the numbers are getting bigger and bigger, that's also sumless. The only ones that you're going to use your formula on is if it's geometric and the ratio is less than 1. In other words, if you're multiplying by a fraction each time. So not a hard assignment at all. It should make sense. Okay? These 6 problems will be due tomorrow, which would be what? Thursday, May 7th at noon. Speaking of tomorrow, on May 7th, Thursday, that'll be the last section of notes for this chapter on sequences and series. Friday, May 8th, make sure you check your Schoology. I'm just going to have a document attached, almost like a letter written to you guys that'll describe what we're going to do those last 2 weeks. It's going to be a pretty easy last couple of weeks. It's just going to be a review as you head to next year of all the different types of functions you've graphed this year. And it'll be a very simplified, short section each day, a very small assignment each day on review of graphing functions, because when you get to your next level next year, you're going to be expected to know how to graph all the functions you've been exposed to. And so we'll just review that topic and make sure you're good to go, and we'll be done. And that wouldn't start till Monday. So make sure you read the document that's attached on Friday, and it'll set up instructions for the last 2 weeks together here, okay? Great job. We'll see you tomorrow.